Hi, today we're going to talk about kinematics. When we look at a graph like this, and I do not want you to write this down, we need to be able to do more than just find out what the displacement of an object is at a given time. So over here we have a graph where we have displacement versus time. And you might have a question that says, can you find the velocity at every point? Now, this is what we're going to talk about, and you will be able to. One thing that I would like to mention before we move on is, notice that the acceleration of whatever object we are talking about is zero. And here's what I mean by that. An acceleration typically changes the velocity per time, meaning that if the velocity at one point was 5 meters per second, then after a second, it might increase or decrease. When we look at these straight lines of a position versus time graph, then you gotta see that the acceleration must be zero. After 1 second, this object has gone, let's say the unit is meters, 1 meter. After another second, again, it has only increased by 1 meter. So you can see that the velocity must be the same since the distance it travels is the same. Now over here, this particular object is not moving. Anything that is not moving typically has an acceleration of zero. So every time you see a straight line for a position versus time graph, the acceleration will be zero, and that's what we will specialize in. Let's look at these equations right here. When you look at the position equation, this is one of the 3 equations we've talked about in the previous video. You notice that we have position equals initial position plus velocity times time plus 1/2 acceleration times time squared. However, this part will go to zero because acceleration equal to 0 meters per second squared, or whatever the units for acceleration is, but the SI units for acceleration is meters per second squared. Now, since that goes to 0, our equation will look like this. Now, if you compare it to a linear equation, y equals mx plus b, which is called the slope-intercept form for a linear function, then you can kind of look at this and kind of compare. If t was the same thing as x of this equation, and the initial position was the same thing as the y-intercept, then the slope must be the same as the initial velocity. So the slope of a distance versus time graph of a line will represent the initial velocity, or the velocity at that time. So let's look at this example right here. If you want to find out what the velocity is of an object that's traveling, that's represented here, then you simply have to just find the slope at every point. Now I numbered them 1, 2, 3, 4, and 5, so we can easily look at one of them at a time. Now this graph can also tell a story. For instance, you could say that Mr. S was trying to go to a picnic and he has gone 3 units in some kind of direction within 3 units of time. Then he hit the brakes at a red light, so his displacement has not gone anywhere. After another 3 units of time, Mr. S realizes he forgot his glasses at home, rushes back home at a faster rate. So I was driving backwards much quicker, but because Mr. S was trying to make the picnic, in 1 second he traveled 7 units of distance. And then he stayed at the picnic, which is why we have a no change in displacement. So these graphs can tell a story. In this particular case, I did not have any units attached. I could have said kilometers. So let's do kilometers here, and let's do hours here. So let's sway away from SI units just for this example, just so we can show some flexibility. These velocities can be found by finding the slope. And to find the slope of this line, you can tell that the speed remains the same between 0 and 3 seconds. The velocity is rise or run. We rise 3, go over 3, so our slope, which is going to be our velocity, will equal 3 divided by 3. But 3 what divided by 3 what? Well, 3 kilometers was the distance, so 3 kilometers per 3 hours, because the units are hours. So the velocity for number 1 will equal 1 kilometer per hour, which are units for driving that we typically use in Europe. For number 2, for the velocity for number 2, same principle, except we don't rise at all. And you should know that the slope of a horizontal line should be 0. A vertical line would have given us undefined, but for a horizontal line it's 0. So our velocity will be 0 kilometers per hour, which matches up to a story I mentioned earlier of Mr. S being at the red light. And then we go down 3, so for our velocity for number 3, we go down 3 over 1, meaning our velocity will be 3, but not really 3, but negative 3 kilometers. I'll go to the negative direction, 3 kilometers per 1 hour, which is just negative 3 kilometers per hour. And I'm just going to go ahead and put pH for kilometers per hour. For number 4, we're going at a very fast rate because within 1 hour we're covering 7 kilometers. So the velocity in this case is going to be 7 over 1 kilometers per hour. And then lastly, the speed for number 5, which is this horizontal line right here. I will not say I want you to decide what that velocity is. So when I check my students' notes, I'm going to be looking for a value right here. Let's look at a scenario where we don't have a displacement versus time graph, but instead we have a velocity versus time graph. And we will have these different graphs that we have to worry about. So for a distance versus time graph, the slope was velocity. For a velocity versus time graph, our slope will be acceleration. And the way I can prove it is just looking at the first equation of the 3 equations. This really looks like y equals mx plus b, and by comparing again you can see that the slope does equal the acceleration. Now to make this more reasonable, just like before, let's attach some kind of units here. Now last time we stick to kilometers per hour, let's go ahead and use miles per hour in this case. So this is miles per hour, and then the time here is hours. So in this case our acceleration, when we find it, should be miles per hour squared, if that makes sense, because we are dividing the velocity by time. So for number 1, we are not increasing the speed or velocity at all within 2 hours. So the slope would equal 0, and the way I can prove it is it's a horizontal line, and a slope would be equaling 0 for horizontal line. We're not rising at all, but we're running, which is 0 over 2, and that would just be 0. So our acceleration will be 0 miles per hour squared. And the way I could write it is miles per hour squared, just like that. For number 2, in 1 second I'm going up or increasing the miles per hour velocity by 2. So I go from 0 miles per hour to 2 miles per hour. So the acceleration in this case will be rise over run, which is 2 miles per hour per 1 hour, which in this case would be 2 miles per hour squared. For number 3, it's a horizontal line. Our acceleration here will also be 0 miles per hour squared, just like for number 1. The reasons are the same. And for number 4, we're going up by 3, and we're going to the right 2. So our slope for number 4 would be rise, which is 3, over 2 run miles per hour squared, which eventually is 1.5 miles per hour squared. Lastly, we have a acceleration between 7 and 8 seconds. Again, that's a horizontal line. And why don't you tell me what the acceleration is at that point? Again, when I'm going to check the notes for my students, they should have something there. So, you tried. I'm going to leave this the way it is. I want you to copy down the graph. For every straight line that you see, you should find acceleration. Alrighty, so I assumed you paused the video and attempted it, and we're going to find the acceleration between 0 and 2 seconds. And that's a slope of 3 over 2, and that would be 1.5 some kind of units. And for units, I'll just go ahead and use meters per seconds for velocity. I'll use seconds for time, so that way I can get SI units, meters per second squared. I'm really comfortable with that kind of stuff, because when we do gravitational problems, our acceleration is 9.8 meters per second squared. So the acceleration between 2 and 4 seconds should have been, and that looks like a terrible 2, should have been 0 meters per second squared, because the horizontal line. Now from 4 to 6 seconds, our acceleration should have been -1 meters per second squared. And then from 6 to 8 seconds, we have a rise of 4, a run of 2, so our acceleration between 6 and 8 seconds should equal, you guessed it, 2 meters per second squared. And that's because I ended up getting 4 divided by 2. And 4 divided by 2 is just 2. And then we have a picture of a dog. So we learned how to find velocity from a distance versus time graph. So let me just go ahead and write this. So from a distance versus time graph, we find velocity. From a velocity versus time graph, we found acceleration. Now we want to be able to do the reverse, meaning once I have a velocity versus time graph, let's not look for acceleration, let's instead look for, you guessed it, displacement. Now I know you want to think that I'm about to point this way and say we're going to find something from this case, but we can't really. When we have a distance versus time graph, the only thing you can get is velocity. However, if you have a acceleration versus time graph, you can get velocity. And let me just emphasize, these are representing average values. We can find the average displacement over a certain amount of time. We can find the average velocity over a certain amount of time. So let's get started. Here's an example. We want to find the displacement of a particle described by the picture to the right. Now, this has to be a velocity versus time graph in order for us to find the displacement. If I find all of this area, then this area will represent the total displacement. So that would give me the total displacement. You can see that if you divide the entire area into smaller parts in which you can easily find the areas, it's not a big deal. For instance, this right here could be looked at as a triangle. A triangle, the area is 1/2 base times height, which in this case is 1/2. The base is 1 second and the height is 2 seconds. So we have 1/2 times base, which is 1 second, times height, which is 2 meters per second. Now again, I'm looking at velocity to be meters per second and time to be seconds. Now, when you calculate this, you also notice that seconds will cancel out and give you a unit of meters. So again, when you manipulate these units, you can really figure things out quite easily. The displacement between 2 and 3 seconds that occurred is just 1 meter. Now that's just a small part of the entire thing. When you calculate the area of this rectangle, then you see that this is 10 meters because you have base times height. And then again another triangle, which is 3 meters, and another rectangle, which is 3 meters. So this can be a pretty fun process because you have to find the area of each part, just add them together, and your total displacement would have been 11, 14, 17 meters. Now, one thing you might want to ask yourself is, what happens if we have an area underneath it? Meaning, what happens if you had something like this going on, right? So what happens with this 1 meters? Well, it is a negative value. When it's underneath the t-axis, it's negative, meaning the total displacement, if you included this part, would have been -1 meters added to the total displacement we had earlier, which would have given us 16 meters. But because this guy wasn't here, neither was the -1 meter. So that should have been your answer for the problem we just did. Alrighty, so this is what I'm going to do in the next video, and I'm going to go ahead and do all of these for you. But you may also want to try them out yourselves to see how far you can get without me doing the video. You have a great day.